We start out with just a little sort of background, primary air pollution and why these aren't giving you something to base this not zero emission vehicles thing on. So we, you see a truck like this and you go, oh, that's pollution, right? And pretty obvious. So those are direct emissions, primary pollutants. But the reason my field of atmospheric chemistry exists is that these undergo reactions in air and they give you a whole host of secondary pollutants. And for the most part, the things that affect our health and climate are these secondary pollutants, not the primary ones. So if we didn't have these reactions in air, life would be a lot different in terms of air quality and air pollution. So, so the key ingredients are mainly, in California especially, volatile organic compounds, and I'll use VOC. So that's gasoline type compounds. It turns out biogenics are an important contributor. So plants and trees, you go into a forest, you get that nice smell, and that tells you there's a volatile organic. Citrus groves, you get limonene. And so as soon as you smell that nice smell, you know that they're putting out these volatile organic compounds. And it turns out most of those, almost all of them, are really highly reactive in air. So it took a while for us to appreciate the fact that there are natural contributions. So the second part is oxides of nitrogen. So that comes, of course, from fossil fuel combustion. So our idea in burning fossil fuels is you combust it with O2, you try to get it to CO2, which we thought was a really good idea for a long time. And out of that, you get energy. But in order to burn it, you need oxygen, and the oxygen comes from air. So you've got nitrogen, 80%, much smaller amount of oxygen. You heat them up to high enough temperature and you get oxides of nitrogen. So most of what you get is nitric oxide and a little bit of nitrogen dioxide. But what happens in air is that this gets converted to nitrogen dioxide. So this was a power plant plume in Provo, Utah at 7 o'clock on a Saturday morning. You can see this brown plume here. So that tells you it's nitrogen dioxide. So we were on our way to Montana to fly fish, and I think 7 a.m. Saturday morning, they thought nobody would pay attention. And when you see something that brown, it means they're putting out a lot of NO, and it's oxidizing very quickly to NO2. And I can show you that. So this is this is a high concentration of nitric oxide I've got in here, and you can see for the most part it's colorless, except my bath. Acetone bath didn't work perfectly yesterday. So if I add, if I open this up, it's under vacuum. And if I open it up and convert the NO to NO2, you can see what happens very quickly. So that's what was happening with the Provo, Utah plant. So one of the things is this color is great, right? So if you think of our sunsets, right? NO2 and particles largely are why we get these gorgeous sunsets. And so many years ago, my husband and I, late husband, were working on our first book. We were up in Washington State, and the big thing was to go hike out to the most northwesterly tip of the continental US to see the sunset. And so it isn't so easy. It's on an Indian reservation and dirt roads, just 2 ruts, and you get out and you park and you got about a mile to walk out and you're tripping over vines and you got your flashlight with you. And we go out there and we sit and we watch. Sun just goes down. And we thought, well, it must have just been a bad day for sunsets, right? And then when we were there for months, we realized we're used to these gorgeous sunsets in Southern California. And this is the only thing I can think of that's good about revolution. So these primary pollutants, these are the things we mainly worry about here. And they react in the presence of sunlight and give you all these other things. So ozone is a major pollutant that smog alerts are called on. We get nitric acid. This is nitrous acid that I'll mention again in a minute. And particles. And I'm going to focus a lot on particles today. So the major driver of this chemistry turns out to be this gas phase nitrous acid. And I have to say, we still don't completely understand where it's coming from, but I'll give you one source today. So this nitrous acid absorbs light, and when it falls apart, it gives you this really highly reactive OH radical. And that's the thing that attacks the VOC and sets off the whole chain. So you don't hear a lot about nitrous acid because it's really a trace contaminant, but it really drives the chemistry. So
It's not the laughing gas, right?
What's that?
It's not the laughing gas.
Yeah, no, not nitrous oxide, no. But that's a good point, because my blood pressure goes up every time I read an article in the paper where they screw up the oxides of nitrogen, and they talk about nitrous oxide or N2O, being a big air pollutant and bad. No, it's a laughing gas. What can I say? So this is also exacerbated. So I've got ozone in here, and you can see that with ozone, you put the laser pointer through, and you can see it reflecting off the edges, but you don't see anything inside, right? So these biogenic compounds, like pinene that you get in a forest. So I'm again going to move this up a little. So I've got some liquid pinene here, and I'm going to put a little bit in here. Oh, so I gotta get this off first. I had this well sealed yesterday, since it was sitting in my office. Didn't want to be gassing myself. So I've got a pretty high concentration of ozone in here. And if I add some alpha pinene, you can see the smoke there. A little more here. So this alpha pinene reacts with ozone, and the reason that it's smoking is it's forming particles. So anytime you can see something like this, like you go in, we don't do this very often anymore, but go into a smoke-filled bar. The reason that you can see it looks hazy, it's because you've got particles, and that's scattering light. So if I put this through here now, you can see the light beam going through, and so it's scattering light, and that's a major reason that particles contribute to climate change. I'll show you in just a second here. So ozone is one thing we really worry about. It's really toxic. It causes inflammation in the lung. Kids in summer camp, they've shown have lung function deficits because of ozone. And they're impacted at levels below the air quality standard. So our standard is 90 parts per billion for an hour, or on the federal 70 parts per billion for 8 hours. And my late husband was a martini drinker. We were trying to figure out, how do you express to the public what a part per billion is? So we did a calculation: how many drops of vermouth would you have to add to a bathtub of gin in order to get a part per billion? And it turns out 1 drop of vermouth and 154 bathtubs of gin gives you a part per billion. So his comment was, "That's a really dry martini." So ozone, we've been doing really well in terms of air quality and improving air quality. California has been the leader, bar none. And so ozone, for example, this is the 8-hour value we're going after, design value. So this is ozone back about 1960, up about 300 parts per billion. You can see it's been coming down, and at the same time, the number of cars has gone up. So it's really a dramatic success story, right? That we've been improving air quality while vehicle emissions and our number of cars have been going up. And of course, it's because of all these things, the catalytic converters, controls of cleaner burning gasoline, and so on. So ozone's gone down by a factor of 3, while vehicle miles have gone up by a factor of 3. So now I'm going to focus a lot on particles. And it took us a long time, I think, to realize how dangerous particles really are. So they really affect every part of the body. So you'd expect that particles are going to affect lungs in a number of different ways. And associated with that, you kind of expect them to hit the heart. But it also causes changes in inflammation and reproductive health. John Wu does a lot of this work. And then central nervous system diseases. And for example, it's been shown in animal studies that they will form plaques that look like the amyloid plaques in Alzheimer's. And there's just increasing evidence of association with things like autism, Alzheimer's, Parkinson's, and so on. And so this inflammation is interesting because back 100 years ago, when people were looking at impacts of ozone on health, there was a study done that included Seventh-day Adventists in Riverside. And it turns out they showed less impact of air pollutants than the rest of the population. And we didn't understand why. And I think we do now, in that, they have such a clean lifestyle that their inflammatory levels are low. And so they have a little extra buffer, right, when they're exposed to air pollutants.
Takes less martinis.
Definitely.
Pure martinis.
Yeah, exactly.
It's higher
Exactly.
ratio.
So the estimate is that 6 to 7 air pollution deaths occur annually due to, and that's just particles, that's not ozone.
But they're also cancer, right? Because some of these particles fix heavy metals and.
Absolutely, and the soot, contains lots of carcinogens, yeah. Why worry about them in addition to that? So the 6 cities study is kind of infamous. So they focused on PM 2.5, so it's particulate matter, 2.5 microns and less. And of course, to put it in context of human hair is about 50 to 70 microns. PM 2.5 is less than 2.5, and PM 10 less than that, 10. So this study really got people's attention. So they did, it's basically epidemiology. So they took 6 cities around the US, from Portage, Wisconsin, which is, I can assure you, is in the middle of nowhere. I've been there. And, don't ask me why. And this is Steubenville, Ohio. So had a smelter. And there's Topeka, Kansas, and these six cities. So they estimated and what the increased mortality rate was. So this isn't like asthma, cancer. This is stone cold dead, right? And they looked at the adjusted mortality rate as a function of PM 2.5. So 1 means there was no increased mortality. But then as PM 2.5 levels go up, you can see the mortality rate goes up. And in fact, when I look at this, I think, I wish my data in the lab were this linear all the time. And it's almost unbelievable, right? So the US standard is 9 here. And the World Health Organization is recommending a standard of 5 micrograms per cubic meter. So, we're way off that, obviously. So what about their trends in LA? So this is, again, the same period of time. And the blue line is the PM 2.5. And that's obviously gone down by quite a bit. At the same time, the number of trucks, which had been a major source of PM 2.5, that's gone up. So it's really the same story as ozone. We've had a big increase in vehicle miles traveled by a lot of these sources, but with the quote controls that have been put on with diesel fuel emission standards and so on, we've made a really big impact on PM 2.5. So particles are bad from the point of view of health, but they're also the big thing in climate. And climate, of course,
both ways, right?
What's
Because
that?
they work both ways. When you have volcanic eruptions, actually, it helps cool off.
yeah, in the upper atmosphere. So that's the whole basis of geoengineering. Yeah, I take a dim view of this, but so you have sunlight coming in and hitting the surface of the earth and putting infrared out, and the natural CO2 and water are there to act as natural greenhouse gases. That means that the average temperature historically, recent memory has been 60 degrees F instead of -2. Without these natural greenhouse gases, we'd all be living like we're in the Arctic. So we rely on these for kind of a moderate climate. But of course, as soon as you put on additional CO2 or ozone or other things that will absorb the infrared, then you start adding more heating. So the particles have been the real challenge. We can calculate the effects of all these gases to a gnat's eyebrow, right? I mean, we know what they do in terms of contributing to warming. The particles are a much more challenging issue. And the reason is they scatter light out. And so that depends on particle size. It depends on composition. It's not even just the average composition of a particle, but if you have a shell around the outside, it can affect it. So it's much more complicated than the gases. The other big thing is that they act as seeds for cloud formation. And of course, you know, if you have a cloud go over on a hot day, you know, you can feel the temperature drop really quickly. So acting as seeds for clouds is a big deal. Both of these things lead to cooling. Now, there are some components of particles that do lead to warming. So soot, for example, and there's something called brown carbon that results from reactions in the particles. So some of them will contribute to warming, but overall, it's really these two processes that are controlling the effects of particles on climate. So this is probably why climate change is more rapid than expected. So back in after World War II, economy was booming. We were burning a lot of fossil fuels. They were high sulfur for the most part. And sulfur, as soon as you have sulfur in the fuels, it comes out as sulfur dioxide, SO2. And that gets oxidized to sulfuric acid pretty quickly, and that forms particles. So what we were doing after World War II is we were forming a lot more particles in air, not putting them directly, but just the SO2 oxidizing the sulfuric acid. And it turns out that that was probably doing this cooling because, you know, we were scattering light from those and they were acting as cloud condensation nuclei. But those particles cause all the health effects I talked about.
Acid rain, right?
Yes, acid rain. So you don't want to be breathing these things, but at the same time, they were kind of masking the warming that was really there all along. So as we've cleaned up sulfur in fuels, gone to low sulfur fuels and done other things to lower particle concentrations in air, now we're seeing the full effect of warming that was always there. And so it's kind of a little sobering. And of course, you know, all the problems. So air pollution and climate change are really part and parcel of the same thing. And we know the effects, you know, Palisades, fires and floods and the wildfire smoke. So a few years back, we were in Montana fly fishing and they had these calendars and it's in the summer, right? So they're trying to sell them for the next year. And this was on the cover of this calendar for Montana. But this is a really strange way to advertise Montana for tourists, right? When you see this, and then we looked at the label.
We're going for Canadians.
Yeah.
That's pretty
Yeah,
good.
right. So this was the annual meeting of Montanans for global warming. So this gets us to this whole thing. Are EVs zero emission vehicles? And the answer is they are not. They are zero emission vehicles, zero exhaust emission vehicles. So ZEEV, zero exhaust emission vehicles. But there are still emissions coming from these things. And they're coming from brakes and tires and resuspension of road dust, for example. So this was a review article where they gave PM10 emissions and PM 2.5. The yellow is the non-exhaust coming from brakes and tires, and probably not so much suspended road dust. That's usually bigger. And then these PM 2.5. And so you see the non-exhaust emissions are often larger than the tailpipe emissions because we've really been cranking down on the tailpipe. And then if you ask, how are these split? Looks like tires and brakes are about the same order of magnitude along with road particles, and then the resuspended dust is much higher, but this is in mass, and the resuspended dust are large particles, so got a lot of mass there. In terms of what happens in a function of year, so this is the percent of non-exhaust emissions that are contributing to the total, and this is averaged over 28 EU countries. From 2000 up to about 2018, and you can see PM 2.5 and PM 10 are both rising dramatically. And here's the 50% mark. So we have certainly passed the 50% mark now.
It's a pre-Brexit slide. We're at 27.
It's so this is from the CARB MFAC model. So they're predicting that exhaust PM 2.5 is doing this and brake wear is doing this. I put a question mark here because there were some studies they based this on, and I think they put too much weight on one that was sort of out of whack and higher. But the point is, anyway, that brake wear emissions are really important. So the kinds of metals you get associated with brakes are iron, barium, and antimony. Those have been chosen as markers of brake emissions. And I'll come back to this in a moment here. So this whole issue of brakes and tires, people are looking at this for a number of years, but it really grabbed everybody's attention when the science paper came out in 2021. And this paper was like a CSI crime thing. I mean, so I wasn't in this field at all and was on my exercise bike in the morning and reading science. And usually I'll just scan something that isn't in my own field, but I started reading this. And it was so good. I had to keep going, even read the SI, right? And so it turns out this group in Washington State noticed that salmon in streams were dying. And the streams, the one commonality was the streams seemed to be close to roadways. And so then they said, okay, maybe there's something coming from traffic that's causing this. And so they did an enormous number of studies to track this down. And what they came up with is this compound that we call short form 6-PPD, that this was the culprit. And what it was doing when it oxidizes, it forms this quinone, this different compound, double bond O here and here. And it turns out this thing is really highly toxic to salmon, some other fish as well. But and what's interesting is that this is added to the tires as an antioxidant. So years ago in California, your tires, your windshield wipers, anything rubber would degrade before you actually wore them out because of attack by ozone. And what's interesting is Avenschmidt at Caltech, who kind of put together he figured out that you needed VOC and NOx to form air pollution. And he was the first chair of the California Air Resources Board, really interesting fellow. I privileged meeting him several times. So turns out what he did when he was trying to figure out what was causing air pollution, he realized ozone was being formed, but we didn't have the measurement techniques in. So what he did is he took rubber bands and he stretched them and put them outside his lab window, and he counted the number of cracks per hour. And then he calibrated it for ozone.
Wow.
Yeah, wow, is right. So there's a little known secret to this whole thing. So now every rubber product we buy has antioxidant in it. And this 6-PPD is one of the major ones. So it's added on purpose to suck up the ozone before the ozone destroys the tire. And it does its job really well, but when it does, it forms this. And then from friction, the tire, gets worn, and the 6-PPD quinone comes off and ends up as runoff in the streams beside the road. So they did a lot of toxicity studies too. So they had roadway runoff and then other water, and this is the LC50 for salmon, and these are the levels they were getting. So there's no question that it was this quinone that was causing it, probably other things too. So I'm sure you all know about this Volkswagen cheating scandal.
German engineering.
Yeah. Well, California fined Volkswagen $86 million, you probably know. And the consent decree said 76 million was to go to the attorneys, of course, for their trouble, and 10 million was to go to research, broadly defined involving vehicles and environmental justice. So the consent decree was signed July 2016. And it said if the research money was not spent in 5 years, it would revert to the attorneys. So they waited for 4.5 years to put out an RFP. I thought nobody would be paying attention. Well, we did. But their attorneys, they don't want to earn research grants. So they didn't want to put out 100 small grants. So you could apply up to 2 million of the 10. So we got 2, and they really funded like 5 big projects from the money. So we know the particles come out. So Don Blake, who I think most of you know, he worked with Sherry Rowland for years, and the senior professor, distinguished professor now on his own, and they do measurements of gases at incredible accuracy and precision, like part per trillion levels at 1% accuracy. And so when we first got this funded, there's 13 faculty involved in this, I'll show you. And when we first got it funded, we had a retreat to say, okay, now we got the money, now we're really going to do, right? And Don says, well, he says, there really isn't anything in this for me because it's all particles, because that's what was in the literature. And he said, I do gases. And he said, I'll tell you what, let me roll around the Roland Hall parking lot on a Friday afternoon when nobody's around, my foot in the gas and foot in the brake, and see what happens. And we'll sample. This was his Toyota truck, which, where he did that. And this is Barbara Barletta and his group who's taking a sample. And so it turns out there were a ton of gases coming out. We couldn't believe it. And so that really led us down a whole path for a couple of years. So then the question is, obviously his, burning his brake pads up is not characteristic of normal driving, hopefully. So we wanted to do things under a more controlled way in the lab. So the question is how to do it. So I have to say I was really naive. And I talked to some of our friends over here in engineering who are part of AirUCI. And when I wrote the proposal, I said, well, we're going to need a dynamometer. And they said, sure, we got a dynamometer. So, okay, so I wrote it in. And then when push came to shove, it turns out there's dynamometers and they're dynamometers. And a brake dynamometer is not what's in engineering. So we had to sort of improvise. And turns out there's a 1943 lathe in our machine shop. And he wanted to get rid of it. So Jim Smith, who's a major player in this and has an engineering background, figured out how to use the lathe as a dynamometer where you could apply different torque and speeds to it and basically try to mimic braking. So this is what it looks like and putting the brakes in. So we did that, and then we've got a million different measurements we can make. So for particles, we can measure the size distribution, the charges, chemical composition, a whole bunch of offline mass spectrometry. Gases, we've got all kinds of mass spectrometry here that we can use, and then these canisters that Don Blake's group does. So this is a canister with Simone and his group sampling. So what did we see when we first did it? Well, it turns out you see a lot. So we did light braking first. Now this is spinning, so we didn't have the brake pads engaged, but the rotor was turning. And it turns out, we're going to go back and look at this because we suspect that there's actually something there. And if that's the case, then that's going to be happening all the time you're driving and may turn out to be the most important part of this. But we were in the machine shop, lots of machine oils and so on. We had a whole thing enclosed in a box that we flushed, but we're very cautious about whether we might have had some contamination from the machine shop.
Because brake pads used to have asbestos.
Yes, so these were semi-metallic and then non-asbestos organic.
Yeah, it went away when we switched from rear driving cars to front driving cars.
Yeah. So I'm not sure, are there any asbestos-based brake pads anymore? Or
I don't think, maybe for vintage cars, but otherwise we're not supposed to.
Yeah, for good reason.
Sell that. Yeah.
So if you start braking, the temperature starts to rise. So this is the rotor temperature, and it's going up here to somewhere around 100 degrees. Then if you really stomp on it, it goes up further and gets up to 200. We've actually gotten up over 300 at times, and other people have reported that in the literature as well. So first you see a little bit of increase here in pollutants, but where you really see it is this heavy braking. And so we got NO2, we got NO, we got VOCs, we got CO. So this really kind of looks like combustion, right? VOCs, NOx, CO. So we get lots of gases, and it's qualitatively similar to tailpipe emissions. So then particles. So these are what our European colleagues did banana plots. So this is the diameter of the particles in nanometers as a function of time. So this is light braking. This is heavy braking, mislabeled here. So this is heavy braking, and the colors represent the number of particles. So red is more particles. So what you see is that with light braking, you form some particles here, but this is 1,000 nanometers. This is a micron. So in the light braking regime, you're forming particles that are roughly 2 microns in diameter from frictional forces. And then in this regime, this is 100 nanometers, and about 50 nanometers is the mode here. So in the heavy braking, you're forming much smaller particles. And we think that's because you're volatilizing things from the brake pad, and they're actually reacting and nucleating to form new particles. So it's very much like what we see in air. So lots of particles generated over a broad range of sizes. So the brake pad composition, you've got friction material, you've got underlayer adhesive, and so on. It's very interesting. Bertha Benz, the wife of the founder of Mercedes-Benz, was the one who first invented the brake pad. And they're ceramic brake pads, the non-asbestos organic. So they don't have that much in the way of metals, but they've got fibers and rubber, carbon compounds, glass, fiberglass, and so on, bonded with resin. So there's a lot of commonality in the composition of these and some tires. So that makes it a little challenging to differentiate them. And then semi-metallic brake pads are a lot of metal components, iron and steel and so on, along with metal fillers. So we took, this is my Subaru, we tried, that was a 2001 or 2002, so it would have more tailpipe emissions that we could look for. So we tried looking at the tailpipe emissions from this using this proton transfer mass spec. So it's an online technique, very sensitive. And what we saw here mainly were these BTEC, so benzene, toluene, ethylbenzenes, and xylene, what you hear about with water pollution. So that looked like a sort of typical, and it was cold start. So we really, pushed it. So this is what in the dynamometer, the ceramic brakes look like, and we got a lot of phenol here, and that's because there's a phenol resin that's holding everything together, and when it decomposes, it forms phenol. You also see acetonitrile here, and I think this is going to be a big marker for brake emissions, but trying to measure it in air turns out to be very tricky. These are the semi-metallic brakes, and so again, phenol you get as a major fluid coming from it. So lots of gases from braking, and they're different from the tailpipe per se. So this is a list of what all the ceramic brake emissions were, the VOC, compared to biomass burning. So if you go down the list here, I'm not going to bore you with all these chemical structures, but anything that ends in ENE has a carbon-carbon double bond, and that's highly reactive. And if you look at these, limonene actually has two double bonds: isobutene, propene, isoprene, methacrylene, ethene, butene. You go down the list, and all these things are really highly reactive. This is a sample of, it's an average from a whole bunch of wildfires, biomass burning, that came out of this paper, Liu et al. And so we connected the same compound. So limonene is number 1 here, it's number 3 here. Propene is number 1 here, it's number 3 here. But you can see that, there's a lot of commonality in the kinds of things that are emitted from braking compared to biomass burning. And so, so we really kind of think that you can think of brakes as kind of like a slow burning wildfire in a sense, in terms of what it puts out. And so clearly these are highly reactive, and they're going to contribute to ozone and particle formation, just like tailpipe emissions have. So one of the things that was interesting, I mentioned this nitrous acid drives the chemistry of the atmosphere largely, and we don't know where it comes from. I have spent a large part of my career on this, and I wish I could tell you I believed I knew where it came from. We don't. But so it starts with NO2, and you can look at all kinds of NO2 reactions, and they do it, but it's slow. But what we did with this brakes is we went looking for HONO, and so this is HONO, and this is where you start heavy braking, and this is ceramic brakes, and this is semi-metallic brakes. So you actually get HONO out of braking. And we haven't been able to quantify how much this might contribute to what's in air, but I think it's probably going to be a significant source that we hadn't appreciated before.
So it's the same scale. So the semi-metallic pads are better from that point of view?
Yeah, so there's less here.
Okay.
Yeah. And which makes sense because they don't have as much organic in them. Yeah.
They don't have the resin, right? Or they don't have the resin that's bonding stuff. That's where it's coming from?
Yeah. So so one thing that's interesting is it turns out that the particles that come out have an electrical charge on them. And so Jim Smith did these studies where he took these particles, so some of them are positive, some of them are negatively charged, and put them into a particle counter. And so it just counts all the particles, doesn't care about charge. And then he put a little electrostatic precipitator in to take out any charged particles and then counted them. So now he's getting the particles without charge, and the difference gives you the number of charged particles. So if you look at them, for ceramic brakes, we were getting up to like 80% of the particles were charged. Semi-metallic, it was about 20%. And it's interesting because if you try to think, how do you control, the tailpipe, we thought was hard, but in a sense it was easy because it's like one point source in a sense, like a power plant. But brakes and tires, you've got the wheel well, it's just not obvious how you're going to capture things from the wheel well. So if they're charged, you can imagine putting a little electrostatic precipitator in the wheel well and capturing a lot of these. So one of the postdocs working on this said, "Got a better idea. Let's put a charge on the whole car, and that'll be a theft preventative too." Oh dear. So there is actually a company in London that's proposing to do this. This is one of their things, and they've kind of gone silent over the last year, so we're not sure what's going on. And so when they presented data a couple of years ago at a conference a year ago, it was collecting significant amounts, but not 100% or anything close to 100%. So these are whole air sampling. These are the canisters Don does. And so we've done an exhaustive analysis of the kinds of organics that are in there. And one of the things we found is that nitrogen-containing compounds are significant components. And we're thinking that this may help us for trying to get a tracer. So these are just some of the nitrogen-containing compounds we've identified in breakware particles. It's just an amazing group, and acetonitrile, as I said, is one that we'd really like to go after, but apparently it's hard to do by GC. So this molecule I'm going to talk a little bit more about. This is dicyclohexylamine. So there's a nitrogen there. And so we thought that would be a really good brake marker. So we have done some field studies. Now I have to tell you, this is not my forte, and I realize how complicated field studies are. But AQMD let us set up right beside the 710 freeway, and the windrows was such that the air was coming mainly from the 710 freeway.
How far from the ports?
What's that?
How far from the ports?
So it would be on that stretch of 710 coming down from 91, probably halfway, something like that. So a lot of truck traffic. Yeah, so mainly truck traffic, really. Yeah.
It decreases
As you go
it
away,
goes from like 20 to 5 or less percent
Yeah.
from the ports.
Yeah, but it's heavy truck
Yeah.
traffic. Yeah. And then we went to the Santa Ana Zoo, and so it turns out that actually it's funny, the fellow who we were put in touch with who arranged this, his name was Mr. Hawk. That's a joke, right? It was. Anyway, yeah. So we were monitoring here, and the wind was basically coming down the freeway. So what we did there is it was really nice. The sound wall of the zoo has some openings like this when they built it, so we can just put our sampling tube through the wall right onto the off ramp. So it's hard to see here, but it's sticking right through the. Well, I really thought Caltrans would see this and come and ask, but they didn't. We were okay. And then this was the 710 site, and the freeway is right behind it. I mean, it's right on top of the freeway. So we did some monitoring there, and we've got Caltrans data on speeds and so on. And so this is the 6 ppd that's characteristic of tire wear. So the purple blue things here. The red line here are the vehicle speeds. And so you can see when things are sort of speeding up, there's kind of a correlation between them. The top is this thing we think would be a good tracer, dicyclohexylamine. So that's the bars. And then the pink in this case is the deceleration rate. So we're thinking that when you step on the brakes, you're going to be decelerating, and that would be a marker of cars actually braking. So this is very preliminary, very.
But there are loop detectors in the pavement.
Yeah.
And you can, depending on where your sampling station is, you can get real-time information about what's happening to the traffic.
And that, I think that's what they did, the
Oh,
students
okay.
did, they,
Okay.
yeah, they pulled that off the Caltrans website that uses that.
Okay.
Yeah, yeah. So, you know, it's, I am not gonna stake my career on this, but you can see that you know, these deceleration peaks are kind of followed by getting DCA, so, you know, if that's related. Now, I have to say, just in the last week, we've come across something that has us thinking, the DCHA is not actually in rubber products or brake linings. It turns out there's it's attached to another core, a thiazole core. And it looks as though what happens is that when you heat things up, that decomposes and gives you this. And so that complicates things, but it also actually, I think, is good because the brakes are the things that heat up more than the tires. So the DCHA is coming, actually, there isn't that much in tires, but you know, if it's coming from both and you have to heat it to get it, then it may be that this would be a good brake marker.
Pads or the discs?
Which the pads.
For the pads.
Yeah, it's the brake pads.
You
Yeah.
know, there is something else that may be of interest. One of our colleagues, Steve Ritchie, worked on identifying vehicles, or maybe you could just have it close to cameras. It would be interesting to see what kind of vehicles really are doing
Yes,
this,
yes.
right?
yes, yeah, absolutely. Yeah.
The cameras would be best.
Yeah. So, so for Long Beach, so what the student has done is asked, okay, we have traces for brake wear that have been reported, iron, barium, and antimony. So she's done correlations between all the things we've measured, and what she's estimating for deceleration. So for iron, you see that iron has a really high correlation coefficient with barium, and that makes sense, you know, from what we know of tire wear particles. The DCHA here is highly correlated, not highly correlated, somewhat correlated with iron and barium, and also with deceleration. So it's you know, again, being a lab person, I normally like to see a lot higher correlations, but these are field studies. So where are we? So EVs are zero exhaust emission, not zero emission vehicles. They emit gases similar to those from wildfires. So it's like a continuous slow burning wildfire. Electrically charged particles, so that gives us some handle to hook to use to try to collect them before they end up in air. And then there's a lot of discussion and controversy about the factors that affect emissions from EVs.
That's the thing. EVs are better because of
Regenerative
regenerative
braking.
braking.
Yeah.
Because everything we were measuring, it was from conventional vehicles.
So I'm, you know, I'm not so sure, because I've seen in the literature people claim just the weight of EVs. I mentioned, you know, this
For the tires, but not for the brake pads.
not for the brakes.
No,
Yeah.
because it's magnetic, right?
Yeah.
Yeah,
Okay.
exactly. They don't use physical.
There's no friction,
brakes.
right? I mean, the friction, you try to apply little of it because it dissipates the energy, turns it into heat. You want
Right.
to recharge the battery instead, right?
Exactly. So period you have to like replace your brake pad is way longer than normal like IC.
Yeah, yeah.
You know.
Yeah.
So it'd be less of a problem?
So
No?
it is that.
I drove someone else's car down the mountain with 150,000 miles on it. She's like, I never changed the brake pads. I was like, oh my God.
Thank you for telling me now.
That was one of the original Priuses that you said, yeah, regenerative braking.
Yeah, but it lasts longer. It does last longer.
Yeah, yeah.
So.
He's not that one.
Probably not. But I mean, it's true that the tire is a big problem, as we were discussing at the beginning.
Yeah.
But I would argue, I don't know, right? For sure, of course, you would know.
Yeah.
That regenerative braking for EVs is a big help.
Yeah, I'm sure it's a big help. Yeah. But I doubt it's going to make it zero.
No, it's not gonna be zero.
Yeah.
At some point, you're
Yeah.
actually braking.
Yeah. You hope.
I mean, with brake pads and.
Yeah. So because we were using this lathe in the machine shop, there was a problem, machine oils and all that sort of thing, worrying about that. And then the machinist wants to sell it and get rid of it. So he keeps saying, when are you leaving? So we, Jim has designed a new portable dynamometer. And the idea is in the first round with Volkswagen, we had 13 faculty involved, including people from Air Pollution Health Effects Lab. So they were looking at the toxicity of the particles, and what they would like to do is have the particles generated and go directly into their exposure chambers rather than collecting particles and extracting and all that kind of thing. And so this is portable so that we can do that. And so Jim calls this the Batmobile, brakes and tires, mobile. And so what we really need to do is go back and look at gas and particle emissions as a function of well-controlled conditions, which we didn't have as much control as we would have liked the first time. And then we really want to make sure we identify these tracers that we can pick up in field studies, do the field and modeling studies to kind of integrate the whole thing together and assess how much of an issue that this really is. And with that, these are the folks that were involved in this Volkswagen money. And it was wonderful because it's really hard to get money to do everything from sort of the chemistry, the physical sciences, to the health effects, to social sciences.
You have two anthropologists there.
I know, exactly.
What
That's
are
what I'm
they
saying.
doing? I mean, I love them and I know Kim.
Yes.
But what is she doing on the project?
So this proposal had to do with, the requirement was it had to do with vehicles and environmental justice, which was not a dirty word at that point. And so they were partnering with Madison Park Neighborhood Association. So we partnered with them, and the Madison Park folks gave us entrees to like the zoo people and monitoring sites and so on. And then we put on a summer program for their students. So Kim and Mike were a really important part of that. And John was looking at trucks and whether we could pick out from satellite data trucks.
Presented that work here, or a student did it, I think.
Yeah. So, and then Mike and Ricky and Andrea, of course, are AFEL, and then these are the folks in chemistry. So the wonderful thing with this money is we could really do all this, and now we're back into being segmented. So, we can get our money for chemistry, but they have to get their own from another source for health effects, and Kim and Mike have.
Why is that? I don't understand.
Because NSF and NIH are really stovepipe.
Oh, yeah. Okay.
Completely stovepipe, yeah. And so chemists, the geosciences people, well, NSF cannot fund anything that's sort of health related, biogenic or health effects related stuff, toxic. So they can fund some things in biosci apparently that are kind of mechanisms of toxicology and toxics, but not what we need to do, right?
Okay.
And so NSF is out for that, and NIH doesn't like chemistry. So
This is crazy. And plus the new administration doesn't like social sciences, so.
yeah, true. So we thank the Department of Justice and
Thank you to
Volkswagen.
German engineering then.
Yes. And then this is a group of people down at the lathe here when we were doing all these measurements. So with that, thank you for your attention here.
That's great. It's very interesting. It's very relevant. I mean, and the state is, I'm pretty sure because we got money from the legislature to do a study. There is an interest in that.
Oh, yeah. Well, the Air Resources Board has its own, they're doing some of their own studies over at their mobile source facility in Riverside.
Yes.
Yeah.
When you were talking about the dynamometer, I was thinking about Matt Barth. He has a big facility where they were doing testing for vehicles, but they were testing exhaust emissions.
Yeah.
But I mean, they had a big space where they were running
Yeah.
axles and everything, so you could probably use that also.
Well, they're actually doing a lot of that themselves.
Okay.
And they're kind of adapting it to try to look at brakes and tire emissions. Yeah. So my sense is CARB is not so interested in putting a lot of money into outside groups because they're putting a lot of effort there. But we're running out of money effective November,
Oh, okay.
and we'll have to stop if we can't find another source. And things through NSF are just not moving.
How about tire manufacturers? Seriously.
Yeah, so actually it's interesting because this fellow Nick Molden, who does these conferences every year over the Beckman
Oh,
Center.
the British person?
Yeah, he has the tire folks there, and they have not indicated that they've actually, a lot of them seem to have their own in-house research programs, so there hasn't been a lot of interest in funding outside groups.
You mean Goodyear or some? some of these
Um,
folks, so.
I'd have to go back there. So there's actually a tire manufacturers association.
Sure.
And so the head of that, and some of their people were there. And then there was a fellow there this last time, a couple of months ago, who says he spent 35 years in the tire field, working for all kinds of tire manufacturers, yeah. But they seem to do their own in-house thing. And we're quite defensive at some of the meetings. Yeah, but it's really hard, right? Because we need tires
Right.
and
But there is, as you know, so they use racing to test new products. And so you have Formula One, of course, for conventional vehicles, but you have an electric version. And I think Michelin is providing their tires.
so you mentioned the F1. So there was an F1 going on in Montreal where the conference was I was at a few weeks ago.
Oh, yeah.
And we were going to send some canisters up and do some stuff like that. But it turns out we couldn't get very close. But then that sparked us to say the Long Beach Grand Prix
Oh,
was
yeah,
on.
exactly.
So
So
we
it
went-
could be perfect,
we
but it's
went-
not Formula One, so it doesn't matter.
Yeah, but we went to that.
Okay.
And the thing is, it's really nice because you can be like right up against the fence.
Right.
And we were right at a corner where they had to brake. And
It's not Formula One, right?
the Grand Prix.
No, right? Yeah.
So, yeah, but lots of braking and high performance
Yeah.
cars and all that. And so Don and his group did sampling and they say lots of organics. There was one organic that we had seen in the dynamometer studies, a gas, methyl isobutyl ketone, that seemed to be characteristic of brake emissions and not tailpipe. And Don and his group have done sampling like everywhere in the world, and he knows when he sees a compound, is this normal or not? It was not, so that looked like a good compound. So they took canister samples and sorbent tube, we don't have those back yet, but didn't see it, or saw it in one sample, it wasn't, so, yeah.
I'm curious, we talked about EV braking technology. What about EV tires compared to?
Well, that's the thing, they are changing the composition of the tires to make
Right.
them harder so that they will not wear out as
Right.
much
Yeah,
and can carry bigger loads. But I think it's evolving, right?
yeah.
They're still doing research on that. That's also why they don't wanna partner up with academia, because you guys are too honest.
So,
Electric racing circuit's a good idea,
Yeah.
I would think, for possible funding.
Yeah, yeah,
sorry,
The electric racing circuit, I
Yeah.
think, is a good idea for possible funding sources.
that's where they do their, they
Yeah,
try new
yeah.
products.
Right,
Yeah.
and you're ultimately telling it a good story, well, it's not zero, it's better, but it is, it's a good story in the political dynamic.
yeah. So this new Batmobile, will let us do tires, the lathe, we could do like a trailer tire.
Okay.
And this will let us do regular sized tires, but quite frankly, there's been so much done on tires, there's so much being done on tires. That we've kind of created our niche with brakes and
Yeah.
we still got a lot to do there, so.
Yeah.
We're anxious to get that defined, but money runs out, won't happen. Yeah. So,
This is really fun.
I know you're not, you said you're not a field expert, but the sensors that you have and use, could they be implemented in the field to do before after studies, after a policy is implemented or a new type of infrastructure is
Sure.
put in place?
oh, sure, yeah.
Okay.
Yeah, so what we have are sort of research grade instruments that take like PhD scientists to run on.
Okay.
So they're
They're
not,
expensive then.
yeah, so they're not ones that you would put out as a regular monitoring tool.
Gotcha. Okay. Yeah, he's wondering how much
But once we identify things, right, and then you can sort of scale back and get techniques that are much cheaper and easier and so on that will, go after specific things. Yeah. So right now, we're just doing this non-targeted, what do we see and what can we pull out? Yeah. All right, yes.
So come on, you're sending it, this project's more like centered on a disc brake, I think.
Mhm.
So did you get any chance to look into some like a drum brake or?
No, we
I
just
think-
did these two types of brake pads.
That's the drums that had asbestos, I
Right.
think. Isn't it the components for the drum brakes that had asbestos?
asbestos?
Yeah,
Asbestos.
yeah.
Yeah, and I think like still like 40% or some like 40-ish% of high duty vehicles in California, like big highways, they're still using drum brakes. So there will be some other like,
Did not know that.
So are those like the medium and high?
Yeah,
I-
sure. And I know some EV use drum brake for their rear tire, because like there's normally their front tire brakes use their their jobs, and rear brakes there's almost nothing to do with, with brakes. So they sometimes use drum brakes in their rear tire as well. So I think it'll be another chance to, like compare
Yeah.
disc brake to drum.
Yeah, yeah. So we talked to AQMD yesterday, and they're interested in this whole issue, but our new Batmobile can do vehicle tires. God bless you. Our brakes, it can do medium, the brakes are used on medium duty vehicles, but can't do, and even that we can't do well, because we just can't get the torque. And we can't do the high, heavy duty trucks, so, yeah, and they're interested in the mix of the whole thing, so, yeah. Yeah, so it's a good point. Yeah. Great, well, thank you very much for the attention, everybody.
Thank you.